Okay, Bismillah ar-Rahman ar-Rahim, wa salatu wa salam ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. Okay, so today we are going to continue the second lecture about Numpy arrays, which is the most important data structure in scientific computing with Python programming language. Okay, and now this slide shows the different data types that are available for Numpy array. Okay, so we have a generic type, which is NP generic, and then it's like class hierarchy. Here we have hierarchy of different types. You have bool for boolean, you have object for classes and object, you have number for different type of numbers, you have date time 64, and flexible, which includes characters, string, and bytes. So under number you have integer, and you have np.inexact. And under integer you have signed integer and unsigned integers. And then you have np int 8, int 16, int 32, and 64. It depends on how much bits every integer type is encoded. And the same thing here, you have it for an assigned integer, so u int 8. Okay, and it's really important to know all these different data structures, because later on when you manipulate data, you need to select some particular types based on the type of task that you will be doing on that data. Okay, and so same thing for np.inexact, you have the floating. So float 16, float 32, 64, up to 128. And you have also complex numbers, which are complex 64, complex 128, and MP complex 256. And you have character, string, and bytes as well. So I provided you a few slides with some code that you can find on the Google Colab, okay, which is about the different data types available. So okay, so here you can see that there are different type of declarations on how you can declare a Numpy array with different types. So you can specify the D type attribute, okay, of float 64 or maybe int 32. So you can do it. Look, this is a float array. You can convert it to another type using as type. So as type allows to convert or to make casting. Okay, it will convert. And look now, you start from float array and you convert it to array, so it becomes integer values. Integer values. Then you have boolean, np.array true, false, false. You can create something similar to this one. It has a type bool. And then you can create a complex using the G symbol, 2 plus 3G here. So this is a Numpy array of complex numbers. And you can create a large array with a small data type, like similar to this one. np.arrange, you know what it's about now. It creates values between 1 and 0 and 999, as you can see over. Okay. And finally here it's inferred type. So if you don't specify the type, you just provide the values. So in this case, it will make an automatic inference about which type is about. So by default here, if you put just integer, it will consider as integer 64. But of course, when you have memory intensive applications, you need to be very specific with yes, because if you don't need to have 64 bits, you are manipulating only, for example, pixels of images up to 255. You don't need to have large amount of memory for only smaller number of values. This is why it's important to understand these data types and to use them. Okay, because it's a matter of efficiency and precision. Okay, if you increase the precision, you will have more less efficiency in terms of computing, because you are going to consume a lot of memory and also computing resources. If you decrease the precision, for example, from float 64 to 16, okay, you'll have better execution time, but less precision. Okay, and if you go to int, it's even this is what we call quantization. Okay, it's going from float to int. You lose a lot of precision, but now there are algorithms that try to minimize the loss with respect to the data type that is selected. Okay, so you have here everything about the data types. And this is an example about the difference between integer data types. So for integer, we have int 8, 16, 32, and 64, and the same thing for unassigned. And the range is different. Now, if you take int 8, it's between minus 128 and 127. Whereas if it is unassigned int, it will be between 0 and 255. So both they have 8 bits. It's encoded in one byte, 8 bits, but the range is different because this is signed, so it can go to different negative values and positive values. So when you have 8 bits, all of them are filled with 1. So in this case, in the case of int 8, it will be 127, or in the other case, it will be 255. Yeah, usually in pixels, we need to have something between 0 and 255. And in some cases, maybe we can take this range. It depends on the problem. And same thing for 16. You can see same thing for int 32, okay, and int 64. And look now the implication. Now, if you take, for example, numpy.unassigned int 8, and you take this vector, which is between 0 and 255, and you add 3. So what will happen here? It will make a rounding up, so 255 plus 3, it will go to 0, 1, 2. Okay? If we do the same operation on int 8, in this case, it will make 127 plus 3, it will go to minus 126. So even the operation will be completely different when you are in the frontier of the NumPy array. Okay, and you can find here in the notebook some more elaboration about these aspects. So here we have an assigned int 8 array. So similar to this one. First time we add 3, we subtract 3, and we multiply by 2. And we do the same thing on unassigned int 8 and also on int 8. So you can see now when we print all the different values, these are the original ones. If we add 3, it will round up to 2 here. If you make minus 3, of course, that's normal. And multiplication by 2, look, it will be 254. So it will go through all the elements until then come back to 0 and start counting again. And same thing here for an assigned int. So for the float type, similar things. We have float 16. We don't have signed and unsigned, so all of them, they are signed. And we have float 16, 32, 64, and 128. And this is the number of significant digits. Okay, and this is for the type complex 64, 128, and 256. So the Python float itself, it corresponds to the NumPy float 64. This is just to see the analogy and the mapping between the Python float type and the NumPy float type. They are different. Okay, they are completely different, but it corresponds to the NP float 64, and the complex in Python corresponds to NP complex 128. Okay. So a very important topic which we talked briefly yesterday is what we call vectorization and broadcasting. And yesterday I made an illustration, but it's important to know again these concepts. So basically they are close in the meaning, but they have some differences. So vectorization here refers to the process of performing operations on the entire array rather than individual elements. For example, we did the example of NP1s 3, 4, and you divided by 5, if you remember yesterday's example. So here, instead of making a for loop and dividing every element by 5, you just need to divide. You just can divide the whole array by 5. This is what we call vectorization. Okay, it's a vector. So this is a vectorized operation. It means it's an operation that can be applied on a vector, not necessarily on elements of the vector. So inherently behind the scene, of course, there will be a for loop, but this for loop is implemented in the C language, not in Python. You don't need to implement this in Python, and we all know that C is basically faster in execution than the Python programming language. So these for loops were made very efficient to execute very fast, and this is why vectorization basically it improves a lot the performance of execution when we deal with large vectors and with different sizes. So same thing here with broadcasting. Okay, is a mechanism that NumPy uses to perform operation on arrays with different shapes. So broadcasting is a particular type of vectorization because here it's not only dividing by a number operation, but you can make operation, add an array with another array with different shapes. Okay, which is not very common, but of course we need to have shape compatibility. The shapes need to be compatible. Now look the difference. If we do a non-vectorized version, so here we need to do 5 operations. Okay, otherwise in a vectorized version you can reduce the number of multiplications. And look now, this is very nice example. We have 3 types of operation on matrices with different sides. This matrix plus this one, and all of them they lead to the same result. Look, in this case, we're going to sum matrices with the same dimensions. Okay, this one plus this one. Okay. Okay, it will lead to. Sorry, I couldn't. If we make the sum. Yeah, okay, let's make the operation here. So this is going to be, the sum will be here, 10 plus 0, 10 plus 1, 11, and plus 2, it's 12. So making the sum of these 2 matrices will result into this one. Now, if we consider this one plus this one only, I don't need to make all of this. Look now, it's only a vector plus another matrix. It will give the same result. Why? Because it will be broadcasted. And this is the example of, this is the meaning of broadcasting. It means you see this in hidden gray color. So this means this operation is going to implicitly be repeated for all these different rows. Okay, this is the normal computation, and this is here we use broadcasting. Okay, yeah, now I understand. This is the operation that we want to do, and this is what happens behind the scene. Okay, so same thing now. Look, I have this vector, and I have this vector. Summing them together, what happens? We will have this vector will be vectorized 3 times for the number of columns, and this vector will be also repeated 4 times based on the number of rows. Okay, and all of them, so if you make one-dimensional vector sum like this, it will result as if you do multi-dimensional vector sum like in the above example. Okay, and this is what we call broadcasting. It means a vector that is going to be broadcasted with all other vectors. But of course, there must be compatibility in the shape. You cannot do broadcasting for random type of shapes. واضح مثال? So today you will have a small assignment to review these concepts. Okay, I shared with you yesterday, but you can do that today because it's based on the concept of vectorization and broadcasting. Is it clear? And this is pretty much needed in deep learning and machine learning for training large models. So another benefit of vectorization, you can save a lot of memory. Instead of having matrices that are complete sizes, you can just have vectors and you can do the same thing. You don't need to duplicate these values into the matrices, into the memory. Okay, that's another example of broadcasting also, similar to the previous one. Okay, so another important concept in Numpy arrays is what we call indexing and slicing, how we slice the elements and extract sub-arrays from a particular Numpy array. And it's very, very flexible. Okay, so we can start by basic indexing and negative indexing. And here the objective is to access a single element with their index, or single elements with their index. And we can use array and we specify the index, and the indexing starts from 0, as you already know. We can also have negative indexing, where the index can be negative. And look now, we start by a Numpy array, which is 4 by 4, which is declared in line number 4 here. And we print it. And now you can access the element at the second row and the third column. Very simple. I take the second row, 0, 1, 2, and third column, it will be, okay, the second row, so it's number 1, index 1, and third column, so it will be 7. Okay, which is 7 here. Now accessing the second last element in the last row. Look, the second last element in the last row, which will be what? This is the last row and the second last element. So this is the last element and this is the second last element. And this is how we express -1, the last row, -2, it's the previous last element. Okay, the second last element, yes. Is it clear? And now we can do also basic slicing. So what does it mean slicing? It's taking part of the array. And we usually use this double column to make the slicing. So what is in this example? Extract the first 2 rows. So we're going to consider all the columns and we extract the first 2 rows, and this is how we do it. So it will take this row and this row. This is how we express it. It's the first 2 rows. And extracting a specific column. Look now. This means that we select all the rows, but the second column or the third column, index 2. And slicing with a step in second row. Okay, so what does it mean? So this is 5 and 7. So what did we select here? We select the second row. So this is how we express the second row. In the second row, it's here, 1. And we select with the steps. Okay, so select 5 and then jump to 7. And we skip 6 and 8. We can try this. Okay, so let's look. It's here. Okay, you can execute this line, and let's try a few examples just down below. Yeah, yesterday I sent you the Google Drive. Okay, yeah, you can send it. Yes, and I invite you, if you want, take 5 minutes and try these different examples. I'm going to stop the record. Okay, so now these are the rules. You have array, you can start from an index, you have the stopping index, and you have the step. Okay, and just read. The first part is about the rows, and the second part is about the columns. So it's kind of filtering rows, filtering columns, and then you will have a subset of the NumPy array. Okay, and look, this is now the general one for multi-dimensional slicing. And this now, what we did here is for two-dimensional array, but we can apply it for multi-dimensional array, 3-dimensional, 4-dimensional, and you specify your conditions for each dimension, for each axis. For each axis, you specify a particular condition: when to start, when to stop, and how much to jump. Is it clear? Okay. So we have also different type of indexing, which is Boolean indexing and fancy indexing. So what does it mean? Boolean indexing, it means that we can do conditional selection, or even we can create masks on the data. We can actually mask some data, remove some data using a mask. Let's see over here the example. You have a NumPy array from 1 to 9, and you want only to select, to make mask data, you only keep the data that is strictly greater than 5. So you can do a mask like this, data greater than 5. This returns a Boolean value, which is true or false, and everything false will be just removed. And this is sometimes we use it to filter some unwanted data or some kind of missing data or invalid data using this type of mask. This is one of the usages. So we can have a filtered data applied to mask. So we apply the NumPy array or this Boolean condition to the NumPy array, and finally it will return the filtered data. Look now, we started from 1 to 9, and the mask was false, 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 true, and finally the filtered data, which is the data applied to the mask, and will return only values that are strictly greater than 5. Okay, so for the fancy indexing, you can have an array of indices. Okay, you don't specify only one index, but an array of indices. So what indices you would like to select? Now we have a NumPy array that have value 10, 20, 30 until 60, and we have indices. I want to select the value number 1 at index 1 and at index 3 and that of index 5. And finally, I apply data to indices. This will be also like a Boolean. Okay, not really a Boolean, but a way on how to index particular elements. And finally, it will return the values at index 1, at index 3, and index 5. Okay, this is how it works. Okay, so we have indexing, slicing, and Boolean indexing. So there is also the concept of masked array. Okay, and masked array here we use the library numpy.ma for mask. And you can create a masked array with a particular condition. For example, every value that is equal to minus 999 will be masked. And this is how to apply. So the masked array here will be 255. Look now, we have a NumPy array of values 1, 2, 3, and this is the undesired value, and 5. So we can think about this as an outlier. Imagine that you would like to make the calculation of the average, and you have some outliers that you would like to remove. What does it mean, outliers? Values that are completely wrong and doesn't make sense. So we can use a masked array, just create a masked array based on the data that you have. It will remove this value, so it will be masked, okay, removed. And the average calculated here will only be for the valid values. Okay, so the average of 1, 2, 3, and 5 will be 275.
So when it removes the value,
yes,
dash dash, is it 0 or is it ignored or is it none?
Which one?
And the
No, it's just like it doesn't exist. It doesn't put 0, because if it puts 0, yeah, it will affect the result. So it's like non-existing data.
So when I do calculation on the array,
yes,
just ignore that value.
Exactly, yes. Okay, so same thing here. We can we applied it to. These are different examples to calculate the mean of temperature and also for rainfalls. These are 3 examples on masked arrays. Okay, I'm going to stop here now, and tomorrow we're going to continue with reshaping and resizing and reading data from